All right. So, we have discussed the idea of regular curves in space. So, let me recall what we have done up till now. So, throughout we have been denoting a curve, a space curve. In fact, its equation is given by r equal to r t. This gives you a vector valued function on a closed interval a b. So, t lies between a and b. And its component, the component of the vector r t are x t, y t, z t. So, when I write x bracket t, in fact, I mean that x is a function of t, y is a function of t, z is a function of t. So, you can see from here that x, y, z are 3 real valued functions on a closed interval a b. And the derivative, if we assume that the function r t is a differentiable function, rather it is regular, means the derivative up to order n exists, we say that curve is a regular curve. So, C is a regular curve of class C n if r t as a function of t is differentiable up to order n and first order derivative of r is non-zero. So, if r t admits derivative up to order n and first order derivative is non-zero for all t in the interval a b. So, this is what we mean by regular curve. So, most of the time we will assume that our curve C is a regular curve. The first order derivative with respect to t we are denoting by the symbol r dot, and this geometrically is a tangent vector to the curve, is tangent vector to the curve drawn at the point t. If you want to look at the components of the tangent vector, it will be dx over dt, dy over dt, dz over dt. These are the components of the tangent vector t. So, whatever point you evaluate, you will be getting the tangent vector at that point. All right. So, for regular curve, we will be assuming that this is non-zero for a regular curve. That is, at least one of the derivatives of x or y or z should be non-zero for a regular curve. Okay. Now, if a curve is not regular, what will happen is either the function r is not differentiable, or if it is differentiable, at some point of the interval its derivative vanishes. So, whatever curve we have seen up till now, let us see which of them is regular and which is not. One of the other important point that I was discussing with you was that there are points t naught says in the interval for which the derivative will be non-zero, will be 0, for example. dr over dt is suppose non-zero at the point t naught. Then this point t naught I will be calling a singularity. This singularity may depend on the either the parameter t or it may be independent of the parameter t. If it is independent of the parameter t, we will call this singularity as an essential singularity. Otherwise, we can change the parameter and the singularity will be removed. We can take up some examples where you can see what are the singularities which are removable and what are essential singularities. Okay. This space curve number 1, in fact, the first example of a regular curve is R t equal to a cos t, a sin t, and some other constant b into t. So, this is the vector equation of a circular helix. Now, you can see that r dot t for any t is given by minus a sin t, a cos t, and b. And if you look at this tangent vector, you will notice that this will never be 0. So, this will not be a 0 vector, and therefore, the helix is a regular curve. Okay. Derivative exists for all t and none of them is 0, and therefore, it is a regular curve. So, we can observe that a circular helix is a regular curve. And some other example, look at the curve, say R t equal to t modulus of t, and you can recognize this is in fact the graph of modulus of t. So, and this has a singularity at the origin. If you look at the graph of this curve in a plane, it looks like this, and this singularity, this has a singularity at t equal to 0. So, this curve C, so C has a singularity at t equal to 0. All other points of the curve are non-singular. All right, and there is another curve, and this singularity is essential singularity. Whatever parameter you choose, you will see it will not go. It is a geometric property of the curve itself, intrinsic property of the curve itself. And there is another important curve that we see. Huh? It's according to the definition, it's not a regular curve. A regular curve is one which admits no singularity at all. For all t, derivative, first order derivative should be non-zero. So, I have got one point t equal to 0 where the derivative is 0. So, according to the definition, it is not a regular curve.
Sir, r dot t will be, we cannot find r dot t here.
R dot t you can't find out.
Because mod.
Yes. So, it
means no need, we can't check even, sir, what is the point at 0 or something.
You see, the derivative does not exist only at t equal to 0.
Yes.
Everywhere else the derivative will exist.
Yes.
So, the problem lies only at t equal to 0.
Yes.
Other points are non-singular points. All right. The other curve is say R t equal to say t square t cube. Okay. So, this will look like a curve like this. and this has a singularity at t equal to 0. It is easy to check, and if you compute r dot at a point t, it will be 2 t and 3 t square. So, at t equal to 0, r dot t is 0, r dot equal to 0. So, t equal to 0 is a singularity, and this singularity cannot be removed. So, it is an essential singularity, all right. But there are removable singularities, that is easy to see. All right, for example, you consider a straight line. I can choose some time a parameter of the straight line in such a manner that there is a singularity with respect to the parameter. Look at this equation. Let me call my parameter to be tau, and I write down the equation some constant a times tau cube, where the parameter tau is defined for all real numbers. Okay. Now, you can see that this, if I consider derivative with respect to tau, then this derivative will be 3 a tau square. So, this implies that r dot at the point tau equal to 0 is 0, and therefore, the parametrization has a singularity at tau equal to 0. Now, sometime you can change the parameter, the image of the curve will not change. So, if I choose some other parameters at t, next choose another parameter t. Okay, so, say r t equal to some a times t, and now t varies between plus infinity and minus infinity. Okay. And this derivative of r dot, derivative of r at t equal to 0 becomes 0. Sorry, a, and I have chosen a non-zero constant a. So, this is a regular point in fact. So, and in fact, no other at no point t, any point t, r dot t at any point t will be non-zero, it is a, and therefore, it is a regular curve. So, this parametrization is regular. So, this suggests that one can change the parameter to avoid the singularity, and what should be the characterization, so that
So, what is the relation between these two parameters then? Means t is t tau cube or what?
no, these are two different parameters. So, t assumes all values from minus infinity to plus infinity, and there is no singularity.
So, both representing the same curve?
No, both are not representing the same curve. So, I am just changing the parameters. So, you can come from t, look, you have an interval, in fact, the entire r, and you can come from here to here through certain maps. So, x over here goes to x cube, okay, Now, this going to the curve, say first curve, second curve, suppose this is the second curve and this is the first curve. Okay. So, the image will be a line here. Now, if I compose these two maps, you will land into the same place. So, now you are coming over here through the map. Suppose this map was something R 1 and this may, let me call it R 2. So, this is R 1 and this is the map, you can call it something R 2. So, this composition is R 1 composition tau. Okay. So, this was a homeomorphism and this is also 1 continuous map. So, the composition of 2 will give you the same points. So, the points will be covered onto the entire R, but this composite map has got a singularity, whereas this has no singularity. Okay. So, singularity can be removed just by changing the parameter. So, this suggests that there should be a method of changing the parameter, so that the singularity is removed. So, we will call this as a, this process we will be calling as reparametrization. Reparametrization. So, suppose we have an interval a b and there is another interval c d. There are two intervals. First, I define a curve C. So, number 1, I define a curve C, which is a map. So, this is a map R equal to R 1 T, where T lies between B and A. Okay. And then I define the same curve through another map, say R equal to R 2 tau. Tau lies between C and D. Okay. Now, if there is a map from A B to C D, let me call it phi, such that phi is differentiable, it is a 1 map. So, this is 1 map such that it is differentiable and its inverse is also differentiable. Then we will say that you can go from parameter t to parameter tau. Okay. And the singularity, suppose it does not have a singularity, then this parameter will also not have a singularity. If you do not have a 1 differentiable map such that inverse is also differentiable, then the singularity will insist. For example, you can see that in this case, this parameter has a singularity, whereas this parameter does not have a singularity, but the map T going to T cube is not a diffeomorphism, because you cannot go from T to T cube differentiably such that this inverse is also differentiable. If phi t equal to, say, phi t equal to T cube, then phi inverse of T will be T to the power 1 upon 3, and this is not differentiable at T equal to 0. So, in order to see whether you can go from one parameter to another parameter, you must check whether you have a map from one interval to another such that it is differentiable and its inverse is also differentiable. The map should be 1 1 also. All right. So, this is how you can consider different parameters. All right. Okay, so I will leave some exercises for you. So, consider check the regularity of the parametrization. For the following curves. Number 1, R t equal to t plus 1 and t square plus 3. Number 2, this is curve number 1 and the second one is R equal to 2a cos theta. This is given in polar coordinates. So, in order to see the regularity of the parametrization, you convert it into Cartesian form. You can write down the x coordinate as well as the y coordinate. X is r cosine theta, y is r sin theta. So, you can convert it easily. And number 3, this I have already done. So, these are the two problems that I am leaving for you. All right.